Good evening, wonderful Wednesday, and welcome to Rask Toronto Centre. We are online tonight, sort of per usual in this day and age. I am Dr. Elena Hyde, the second Vice President of Rask Toronto Centre, and this is our January Speakers Night presentation. Very exciting, the first talk of 2022. As a reminder, this is one of two types of gatherings that we have online these days. We are still not at the Ontario Science Centre due to the pandemic. Later on tonight, our president, Tom Luton, will be talking about various programs. But first, we have a very special event to kick off tonight. Now, since this is 2022, what better way to get ourselves started than by actually taking just a moment to acknowledge that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territory of many Indigenous nations. This includes the Haudenosaunee Confederacy, Huron-Wendat, the Mississaugas of Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. So, as we engage in astronomy here tonight, together we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, the earth, and in fact, the universe, as you may remember, we learned from Will Morin just last year. So, speaking of the universe, and in particular the early universe, that actually gives me an excellent segue into our speakers' night tonight. I am absolutely delighted to welcome Sunna Withers. She is a BSc Honors and just this last year, and now she is a current MSc candidate at York University. So, our fantastic speaker, Sana, is a long-standing member of the Alan I. Carswell Observatory, a wonderful place, if I don't say so myself, just a little bit biased. Now, Sana has participated in the observatory's variable star research even before doing her master's. She's been an expert user of our 60 centimeter telescope and public outreach of all kinds. So I'm really thrilled to see what she brings to the talk tonight here at Rask Toronto Centre. Sunna was one of our all-time most enthusiastic and skilled telescope operators for public outreach and astrophotography, and she was actually in the domes on the day the 1 meter was installed, and I believe there for the evening of first light as well. So I am really excited to see what mysteries that Sunna will bring to us from high redshift galaxies and the early universe. So without further ado, Sunna, please take it away.
Hi. Hi, everyone. Thank you for having me. I'm very happy to be here talking about high redshift galaxies. I figured this was the perfect topic to talk about given the recent launch of the James Webb Space Telescope. Before I get started, just a quick outline of the talk. I'll start off with an introduction, then move on to talking about how we observe high redshift galaxies, then our current understanding of the high redshift universe, and finally, what we can expect in the coming years with the amazing new telescopes that are set to come online. So I'll start off by defining a word that I've used a couple times already, which is redshift, represented by a lowercase z. In the most general terms, the redshift just describes how much the light coming from an object is stretched out and shifted towards redder wavelengths. There are quite a few different ways that light can be redshifted, but the one that's relevant to what I'm about to talk about is how the expansion of our universe redshifts light coming from distant galaxies. Our universe is expanding, it always has been, and as the universe expands, it causes galaxies to move away from each other at very, very high speeds. And this essentially just stretches out the light coming from a galaxy and redshifts the light that we observe towards redder wavelengths. It turns out that redshift is a very, very useful thing to measure because it tells us two important things about a galaxy. So first of all, redshift is a measure of distance. The higher the redshift, the more distant the galaxy, and galaxies that have the same redshift are the same distance away from us. And because redshift is a measure of distance, it's also a measure of time. Specifically, what redshift tells us is how long it took the light coming from a distant galaxy to reach us. This is called a galaxy's look-back time, and it essentially just tells us how far we're looking into the past when we observe a galaxy. Since, of course, we don't observe things the way that they are now, we observe them in the past when their light was emitted. Then, because we know how old the universe is, we can use a galaxy's look-back time to figure out how old the universe was when that light was emitted. And that's kind of the key thing to remember here, is that the redshift tells you the age of the universe that you're looking at, so the time since the Big Bang. I have a couple numbers on the screen just for reference. Redshift of 0 is today, where the universe is 13.8 billion years old. If you go out to redshift 1, the universe is about 6 billion years old. And if you go all the way out to redshift 6, the universe is about a billion years old. So if you want to observe the universe at different times, you observe galaxies at different redshifts. And this is a pretty useful thing to do because the universe didn't always look the way it does today. So by observing galaxies at a variety of different redshifts, you can essentially observe the universe as it evolves through time. And this has been done. Astronomers have been observing galaxies at a variety of redshifts for many, many years. They've then coupled those observations with some other ones, mainly of the cosmic microwave background, to give a sort of picture of the way that the universe looks over time. One of those is shown here on the screen. It identifies 6 important epochs of the history and evolution of the universe at the top, along with the redshifts that they happen at, and then the age of the universe at each of those times in billions of years along the bottom. And before I start talking about high redshift galaxies specifically, it'll be useful to go over a brief summary of how our universe, the early universe specifically, has evolved. So when I say early universe, I just want to point out that I'm specifically talking about roughly the first billion years of cosmic history, so redshifts 5 to 6 and above. There are some very interesting things that do happen at lower redshift, but this is about the early universe, so that's mainly what I'm going to focus on. And another note is that when I say high redshift galaxies, I mean galaxies with redshifts of about 5 and up. Some astronomers might disagree. Others consider redshifts 1 to 2 to be high redshift. But in this talk, I'm specifically referring to galaxies with redshifts of 5 and above. So starting all the way back with the birth of our universe and the Big Bang, during the Big Bang and directly afterwards, the universe was very, very small. So all of the matter and energy and everything in our universe was packed into a very small region. That made it very dense and very hot, which made the conditions in the early universe very, very extreme. It was so extreme that the matter that we're used to dealing with just didn't exist in that state. We're used to dealing with neutral matter when we just in our day-to-day lives, and even when we observe distant galaxies. But matter just didn't exist in that state in the early universe. But like I said before, the universe has always been expanding. It has been since the Big Bang. And as the universe expanded, it became less dense and it cooled down. And over time, various things happened, and the matter started to form in a state that we're used to seeing. So one of the first things that happened is that fundamental particles like electrons and quarks became stable, so they could form and stick around for long periods of time. Then after that, the conditions cooled even more, so that quarks could form hadrons like protons and neutrons. Then eventually some heavier nuclei formed, primarily helium and small trace amounts of lithium, but nothing heavier than that. And at this point, the universe was like a soup of charged particles, which we call ions. It was still too hot for neutral matter to form. So you just had a bunch of ions kicking around, electrons and protons mainly, that couldn't form neutral matter. But if you fast forward to around 380,000 years after the Big Bang, or a redshift of about 1,090, the universe had finally cooled enough so that those electrons and protons could combine to form neutral matter. This event is called recombination. If you've ever heard of the cosmic microwave background, recombination is what released that radiation. It created the cosmic microwave background, and there's an actual little picture of the CMB radiation right here. And another important thing that happened at recombination is that it began the next epoch of evolution in our universe, which is called the Dark Ages. So at this point, the universe is filled with this neutral primordial gas. So when I say primordial, I mean primarily hydrogen, about 75%, about 25% helium, and then small trace amounts of lithium. At this point in time, there were no stars or galaxies or any of the large-scale structure that we see today. So you might not think that there's a lot going on in the universe at this point. But something very important was happening, which is that density fluctuations from the early universe were starting to grow. If you look at this map of the CMB here, you see these blue regions and red regions, which represent density fluctuations. Red regions are areas of overdensity where there's more matter than on average, and blue regions are areas of underdensity where there's less matter than on average. And around the time of the cosmic microwave background and recombination, those density fluctuations were incredibly small, about 1 part in 100,000. So the universe was incredibly uniform in density at this point. But over time, because gravity is an attractive force, those overdensities started to grow during the Dark Ages. So regions of overdensity became more overdense, regions of underdensity became more underdense. And eventually, this laid the groundwork for all of the large scale structure that we see in our universe today. And it also led to the formation of the first stars and the first galaxies. At a redshift of about 20 to 30, which is only a few hundred million years after the Big Bang, these density fluctuations had finally grown enough so that the first stars could form. This is called cosmic dawn, where the first stars in our universe finally turned on. The stars that formed during cosmic dawn are called population 3 stars. And because they're made out of this pristine gas, they have properties that are very different from stars from later generations of stars like we see now, like our sun. The primordial gas allowed them to grow much, much larger than stars that we currently see. They could reach masses of up to 1,000 solar masses by current estimates. That made them much more luminous than our sun, and also made it so that they had incredibly short lifetimes, only a few million years, if that. And once a few million years had passed and these population 3 stars died, they blew up in supernova explosions and started chemically enriching the universe. Astronomers call anything heavier than hydrogen and helium a metal. So when stars during their lifetimes, they form metals, they form heavier elements. And when stars die, they eject those elements into the gas surrounding them and galaxies, which is called the intergalactic medium, or IGM. And once population 3 stars died, they, for the very first time, chemically enriched the universe by ejecting the metals that they had formed in their cores during their lifetimes into the intergalactic medium. So from then on, population 2 stars formed, which is the next generation of stars after population 3, which are not formed out of pristine gas. The cosmic dawn is related to the epoch of reionization. At around redshift 12, cosmic dawn transitioned into the epoch of reionization. And there's a couple important things that happen during this time. So first of all is that the first galaxies start to form and grow. And another important thing that happened is that the universe transitions from being mostly neutral to mostly ionized. So around cosmic dawn and right before that, the universe is just filled with a neutral gas of mainly hydrogen. But when the first galaxies and the first stars form, they start to emit light that's capable of ionizing hydrogen. So this ionizes the intergalactic medium, the gas between galaxies. It starts at around cosmic dawn, when the first population 3 stars form, and you have these very small pockets of gas, like you can see in this figure, that are embedded in a larger volume of neutral hydrogen. But over time, as more galaxies form and more stars form and galaxies grow, you get more of these pockets of gas and they start to grow. And eventually you transition from a mainly neutral universe to a mainly ionized one. And you can have some small pockets of neutral gas surrounded by mainly ionized gas. That happens at around redshift 6. And when you get to a redshift of about 5.5, the universe is primarily neutral, about 99.99% ionized. I said neutral before. I meant the universe is primarily ionized at redshift 5.5 by about 99.99%. So with that summary of the early universe, I'll talk a little bit about how we find high redshift galaxies. There have been quite a few galaxies found during the epoch of reionization. Roughly speaking, there are hundreds to thousands over redshift 6 to 8, even more at lower redshifts. But when you get to redshift 8, there are very few known high redshift galaxies. There's maybe about 10 to 20 of them at redshifts greater than 8, with the highest redshift galaxy that has ever been discovered at redshift 11.1. It's called GNZ11. Typically, when you want to find high redshift galaxies, you have to do two things. So first of all, astronomers take photometry of the galaxy. So they just directly image the galaxy in multiple different filters that cover different wavelengths and use that to get an estimate of the galaxy's redshift. Then after that, they do follow-up observations of the galaxy to observe it spectroscopically. So they take a spectrum of the redshift of the galaxy and use that to determine its redshift. You have to do that spectroscopy because the redshifts determined using spectroscopy are a lot more precise and reliable than redshifts determined using just photometry. So that is a very important step in identifying galaxies. High redshift galaxies are very, very dim. The ones that we've discovered have magnitudes sometimes dimmer than 29 to 30th magnitude. So if you want to observe these, you have to use the deepest, most detailed images of our universe to find them. And those images are provided by deep fields. Deep fields are quite common now. There have been many taken. Very popular ones come from the Hubble Space Telescope. And what these deep fields do is they just stare into a small region of primarily empty space and try and find some of the dimmest galaxies that are there. So, like I said, a lot of these deep fields come from the Hubble Space Telescope, and they're probably the most popular, possibly most useful ones. So, I'll talk a little bit about those deep fields. The Hubble Space Telescope was actually responsible for taking the very first deep field in 1995. And while deep fields are quite common now, and Hubble has done many of them, in 1995, this was a very odd thing to do. It was proposed at the time by the director of the Hubble Space Telescope, and what he wanted to do is just figure out what they can get out of Hubble. He wanted to figure out what the dimmest objects were that it could detect and how far away it could see. So he took a bit of a backwards approach to observing. Typically, when you want to observe something, you pick a target, something that looks interesting that you want to learn about, you point the telescope at it, and you observe and get your data. But he wanted to do the complete opposite. He wanted to take the telescope and point it at absolutely nothing and see what the telescope could find. So what they did is they picked a region of sky, a very small region of sky, about 1/12 the size of the full moon, which had pretty much nothing in it. There were no bright galaxies, no bright stars in our galaxy. They picked a region right above the Big Dipper because it satisfied both of those requirements and pointed the Hubble Space Telescope at it for 10 days straight, taking observations in 4 filters that cover visible wavelengths. And the result is this picture on the screen. This is the original 1995 Hubble Deep Field. And if you take a closer look at this image, what you see is a ton of galaxies. You might see 1 or 2 bright, dim stars from within the Milky Way galaxy. But apart from that, every point of light in that image is a galaxy, which is exactly what the director of the Hubble Space Telescope wanted to accomplish. This image was completely revolutionary for astronomy because it was the deepest view of the universe at the time. It found both the faintest galaxies that have ever been detected and the highest redshift galaxies that had ever been detected at the time. It found galaxies up to a redshift of about 4, which is about 1.5 million years after the Big Bang. So they could get a lot of very, very interesting data about high redshift galaxies from this and how galaxies evolved over time. They ended up also doing a second deep field not too long after the original deep field was taken in the southern sky, which was named the Hubble Deep Field South. And then this was named the Hubble Deep Field North, just to keep things straight. And they got very similar results using the southern deep field, an image just packed full of very, very dim and very, very distant galaxies. Given the success of the original Hubble Deep Field North and South, Hubble went on to do many more deep fields, where they went not only to deeper, dimmer and dimmer magnitudes, but they also included other wavelengths of light. The Hubble Space Telescope primarily looks at visible light, but it also has some coverage in the ultraviolet and infrared wavelengths. So they did some deep fields that include those. The infrared deep fields are particularly important for high redshift astronomy, just because the light coming from high redshift galaxies is often redshifted out of the ultraviolet and visible and into the infrared. So there are some high redshift galaxies that are just not able to be observed in visible light, and you have to use infrared. So those infrared Hubble deep fields are very important for high redshift astronomy. A couple of the other deep fields it did was the Hubble Ultra Deep Field, which observed a small patch of sky for about 11 days, reaching redshift 7 galaxies. Then there's the Hubble Extreme Deep Field, which is abbreviated as XDF, hence the weird spelling of extreme here. And that's what's shown on the screen here. This Hubble Extreme Deep Field incorporated observations taken over a decade. There's a total 50 days of integration time that were not all taken at once, and it included infrared images. So the depth of this photo combined with the infrared wavelength coverage allowed it to find galaxies at redshift 11, which is our current observational frontier. No galaxy above redshift 11 has ever been found as of today. Hopefully that will be changing soon. And finally, the most recent Hubble Deep Field that has ever been done is the Hubble Legacy Field. The Hubble Legacy Field is not as deep as the Hubble Extreme or Ultra Deep Field. It covers a much wider range of sky. So they weren't able to go as deep just because of timing constraints. Yeah. Now, in addition to the Hubble Space Telescope, many other observatories have also done their own versions of deep fields. And often what happens is that more than one telescope observes the same field. This is a very useful thing to do because when you have multiple telescopes that have different wavelength coverages observing the same field, you get a more complete picture of what's going on with the galaxies that are in that field. So different wavelengths of light tell you different things about a galaxy. So for example, ultraviolet and visible light tell you about star formation and the young stars that are in a galaxy. Infrared light tells you about the older stellar populations in a galaxy. And X-ray or gamma ray light tells you a little bit about the high energy events going on in the galaxy. So if there's any activity surrounding a central black hole, X-ray and gamma rays can tell you a lot about that. So if you want to get a full, complete understanding of what's happening in a galaxy, you have to incorporate multiple observations at multiple different wavelengths. A very good example of this is the Great Observatories Origins Deep Survey, or GOODS. The GOODS survey gets its name from NASA's Great Observatories, the Hubble Space Telescope, the Spitzer Infrared Space Telescope, the Chandra X-ray Telescope, and the Compton Gamma Ray Observatory. And what they did in the GOODS fields is all of these telescopes, combined with many other ground-based telescopes, including radio telescopes like the Very Large Array, observed the same patch of sky, which is shown in yellow on this figure here. It has two fields, one in the north and one in the south. Each of them is about 16 by 10 arc minutes approximately, or about 20% the size of the full moon. And each of these fields has been observed by multiple different observatories. The included in that is the Hubble Space Telescope. So there are two different ways that Hubble observes the GOODS field. First of all, you can see it contains the extreme deep field and the Hubble ultra deep field, and then also the the much wider area Hubble Legacy field around here. The GOODS survey has been particularly useful for high redshift astronomy. They've produced many, many amazing observations for many different fields of astrophysics. In particular, for high redshift astronomy, they have found hundreds of galaxies during the epoch of reionization. And its data is actually still being analyzed today to try and find more galaxies within this field. And the data is also being continually updated from observations from space and ground-based telescopes today. In fact, many of the highest redshift galaxies, so at redshifts greater than 8 or 9, have been found in the GOODS fields. And this includes the highest redshift galaxy ever detected, GNZ11. It was found, there's a picture of it right here on the screen. You can see how small it is because it's from this area. This is just a zoomed in view, but it appears incredibly, incredibly small in this image. And it was originally detected by looking at imaging from the Hubble Space Telescope and the Spitzer Space Telescope, and also includes observations from several other observatories because it's in the GOODS fields. Now, combining all of those deep field observations and many other observations has now given us a picture of what the high redshift galaxies look like. And I have a bit of a summary of their properties here. So just going over some of those. High redshift galaxies generally are small and compact. They have sizes typically less than 1 kiloparsec in diameter. And for reference, the Milky Way galaxy is about 30 kiloparsecs in diameter. So these galaxies are incredibly small. Their star formation is also located towards the center of the galaxies. It's not really in the outskirts like you would see in some lower redshift galaxies. They also tend to be low mass and dim. It is possible to have high mass and luminous galaxies in the high redshift universe. Those are actually some of the more commonly observed than the low mass and dim ones because they're just easier to find. But current estimations do show that low mass and dim galaxies vastly outnumber luminous and high mass galaxies. So they kind of dominate the high redshift universe. They also tend to have irregular morphology. These aren't disturbed morphologies like you would see between collisions between galaxies, but they don't follow the Hubble sequence of morphology. So you won't see galaxies that are spiral with disks or any structure in them, and they tend to just look irregular. I have a picture here of 28 galaxies from the Hubble Ultra Deep Field that are at high redshift. And you can see from all of them that they do all tend to look fairly small, fairly compact, and none of them have a really well-defined morphology. Moving beyond what high redshift galaxies look like, a lot of them, or they generally do tend to have very high star formation rates. This is likely because they're in the process of growing, so they're accreting gas from their surroundings, and that really feeds their star formation rates and drives it up. Because they have been forming stars, they tend to be dominated by these young stellar populations, so very massive, young, hot, and blue stars. This also means that they are fairly metal poor with little dust, since they just haven't had time to undergo a lot of chemical enrichment. So these galaxies they generally don't contain population 3 stars, they contain population 2 stars. So they have been chemically enriched, but just not as much as we would be seeing at lower redshifts. And then all of these properties from high redshift galaxies are reflected in their spectrums. So high redshift galaxies tend to be very blue and have strong emission lines just because of the young, hot stars that emit a lot of blue light, a lot of high energy light that makes their spectrums blue with strong emission lines. One thing I will point out here is that if you look at the pictures on the screen, I just told you high redshift galaxies are blue, but all of these are red. And the reason for that is just because they've been redshifted, had their light redshifted to these wavelengths. But if you were to account for the redshifting effect, they would appear blue. So since high redshift galaxies have properties that are fairly different from lower redshift galaxies, and because they live in a different environment than lower redshift galaxies do, there are a couple new kinds of galaxies that we find at high redshift. One of those are Lyman break galaxies. These are incredibly common at high redshifts. And a Lyman break galaxy is just characterized by a very strong and sharp decrease in the flux coming from a galaxy at wavelengths shorter than about 1216 angstroms. And this is just caused by the fact that there is a ton of neutral hydrogen in the early universe. Light with a wavelength of 1216 angstroms and shorter than that can be absorbed by neutral hydrogen. It can either excite the electron in a hydrogen atom or it can ionize it. And what happens is that when high redshift galaxies emit neutral hydrogen, this light eventually runs into a neutral hydrogen atom and gets absorbed. So even though galaxies are emitting light with wavelengths shorter than 1216 angstroms, wavelengths bluer than that, we don't see any of that light because all of it gets absorbed by the neutral hydrogen that surrounds galaxies. I have an example of a Lyman break galaxy on the screen here. This is data from galaxy GNZ11, which I talked about a couple slides ago. And there's a few things going on in this slide that I can explain. So first of all are these few images here. These are images of GNZ11 using the Spitzer Space Telescope with this picture here, and the 3 reddest filters on the Hubble Space Telescope right here. The photometry for that galaxy, so its brightness and its magnitude, are also reflected on the graph here in the red points. And then this gray line here represents the spectrum that we would expect for GNZ11 based off of those images in different filters. And you can notice here the Lyman break is right here. The Lyman break in the rest frame is at 1216 angstroms, but since this galaxy is at a redshift of 11, that Lyman break or 1216 angstroms has been redshifted to 1.4 microns, which you can see here. And then you can just look at the images and the spectrum and the photometry, and you can see that at wavelengths redder than rest frame 1216 angstroms, there's a very strong signal coming from the galaxy. You can even see some emission lines in the spectrum. You see it in both of these pictures. But then when you hit the Lyman break, the brightness of the galaxy just decreases pretty much immediately, and it disappears from the pictures. And that is the characteristic thing that Lyman break galaxies do. And it's very common for astronomers to look for this signal in high redshift galaxies because it's a very common thing. Another kind of high redshift galaxy are Lyman alpha emitting galaxies. The Lyman alpha line is at 1216 angstroms, so the same wavelength as the Lyman break. And Lyman alpha is indicative of star formation, so galaxies that form stars tend to emit a lot of Lyman alpha. High redshift galaxies are forming a lot of stars, so they emit a lot of Lyman alpha as well. One issue that you can see with Lyman alpha emitting galaxies is that I just told you that that wavelength of light gets absorbed by neutral hydrogen surrounding galaxies. And it's true that it does. So one problem with the Lyman alpha emission line is that even though it's present in high redshift galaxies, we don't always see it because it gets absorbed by the neutral hydrogen around it. It's a line that's very, very sensitive to what is happening in the gas surrounding the galaxy. So sometimes we don't always see that Lyman alpha, even though it's there. Related to Lyman alpha emitting galaxies are extreme emission line galaxies. So these galaxies are caused by the fact that high redshift galaxies have very young metal poor stars. They emit very strong radiation fields. And from that creates very strong emission lines in the rest frame, visible and ultraviolet. So these are things like oxygen 3, hydrogen alpha, and even Lyman alpha as well. These emission lines in some cases can be so strong that they emit more than half of the light coming from a galaxy at a certain wavelength. And this is something you just generally do not see at lower redshift. This is a distinctive property of high redshift galaxies. And it's they're also very common at high redshift as well. They can dominate the galaxy population, sometimes reaching over 50% of the galaxy population at high redshift being extreme emission line galaxies. And the last kind of high redshift galaxy I'll talk about are dusty star-forming galaxies. These galaxies have extremely high star formation rates, about 1,000 solar masses a year, which is incredibly high. So they're starburst galaxies. But they also have a lot of dust. And this dust just absorbs all of the visible and ultraviolet light coming from the stars. So you really don't see them in ultraviolet and visible wavelengths. The dust absorbs all of that. It heats up the dust, and then the dust re-emits that radiation in the far infrared. So you can't really observe them in visible or ultraviolet light. You have to observe them in far infrared or radio observations for high redshift galaxies. Apologies. All right. So although there is a lot known currently about high redshift galaxies, there are many things that we don't know. So a couple questions that are remaining about the high redshift universe I have them listed on the screen. So first of all, we don't know too much about the formation and evolution of the very first galaxies. We know that galaxy buildup was underway by about redshift 10 because there are massive galaxies that exist there. But apart from that, we don't really know a ton about what's going on at this time. We don't know how the first galaxies formed. We don't know how they evolved, how they built up their mass. So there is a lot to be learned about the physics of star formation and the physics of galaxy evolution at early times. Does it change over time, or is it the same as it is at lower redshift like today? We don't really know, and this is still an open question. There's also a lot we don't know about the epoch of reionization. We know that it started at around redshift 10 to 12, and it's ended by redshift 6, but we don't really know what happens in between. So, for example, was reionization early? So it was completed in the earlier days, finished maybe closer to redshift 8, and then it slowly finished off to get to redshift 6? Or was it slow, where the early days of reionization, not too much happened, and then it very quickly completed closer to redshift 6? We also know that the galaxies responsible for reionization have to be very small and dim galaxies. We know this just because of the process of elimination. Massive luminous galaxies are not common at high redshift. There is not a lot of activity surrounding supermassive black holes at the center of galaxies in the early universe. So really the only option for reionization are these small dim galaxies. But these haven't really been observed is the issue. So we need to observe this galaxy population that reionized the universe, and we also need to characterize them, so figure out what their properties are. So practically, the way that a lot of these questions are solved is by just observing more galaxies during the epoch of reionization. We need to expand the sample sizes over redshift 6 to 8. We need to massively expand the sample sizes for galaxies above redshift 8. And we also need to find the first galaxies at redshifts above 11, which is the current observational limit, because we don't see any galaxies there. We don't really have a clear picture of exactly what is going on. Finally, the last question that I'll mention is surrounding population 3 stars. These are the very first stars in our universe, and we can learn about them just based off of what we know about star formation and the conditions in the early universe. But these stars have never been observed. They are too dim for us to observe. They're very, very luminous, but they're also very far away, so they're too dim for us to see at the moment. And they also don't live very long. So it's really not possible for them to still be around today as far as we know. So we don't really know what the properties of these population 3 stars are. They've yet to be observed, they've yet to be characterized, and that's something that we need to do before we can say much of anything else about population 3 stars. We're at the limit of what we can figure out about them theoretically, is the point. The reason that many of these questions remain today is because we just don't have the facilities to be able to properly answer these questions. There have been kind of a lack of new facilities launching and coming online that we really need to understand these questions. But hopefully that will change in the 2020s to 2030s, because there are many amazing next generation telescopes that are set to come online during that time. I'm going to talk about 3 of them today. There are many, many more, but I'm just going to focus on these 3. The James Webb Space Telescope, the Nancy Grace Roman Space Telescope, and the Square Kilometer Array. So starting with the James Webb Space Telescope, I've got a picture of it on the screen here with a human for scale. This is the largest and most complex space telescope that has ever been created. It is really an amazing telescope. The engineering of this telescope is totally mind-boggling. It's a 6.5 meter, it has a 6.5 meter diameter primary mirror, and it's an infrared telescope that covers the near and mid-infrared wavelengths, so about 1 to 28 microns. It's a joint mission between NASA, the European Space Agency, and the Canadian Space Agency, so there is a connection to Canada with this telescope. Canada's contribution was one of the 4 instruments on board, which is the Near Infrared Imager and Slitless Spectrograph, or NIRISS, which also contains the fine guidance system that Webb will use to point. It launched on December 25th, 2021, and currently all of its major deployments are complete. It had to be folded up to be put inside the Ariane 5 rocket and then unfold itself when it got to space, and all that is complete. It also has 18 hexagonal mirror segments that all have to kind of come together to work as one giant mirror. And as of today, the major movements of all of those segments are complete, so they just have to be aligned. The full alignment of the mirrors on this telescope is going to take an additional 3 months, following which various instruments and everything have to be characterized and tested out. So it's going to take approximately another 5 months for the James Webb Space Telescope to finish commissioning, and we're expecting to get the first pictures from the telescope in a late June, early July, so about 5 months from now. This telescope is going to be completely revolutionary for many, many fields in astrophysics, including high redshift astronomy, and this is for 2 reasons. First of all is its wavelength coverage. Webb covers the infrared wavelengths, which you need for high redshift astronomy because light from distant galaxies is often redshifted into the infrared. So Webb is going to be able to observe these infrared wavelengths and open up a new window on these high redshift galaxies that have been closed to us before. And another reason that Webb is going to be revolutionary is just because of the mirror size. It's a 6.5 meter diameter mirror, several times larger than the Hubble Space Telescope and the Spitzer Space Telescope, which was an infrared telescope as well. So it's going to be able to collect a lot more light than those telescopes and see dimmer objects. The larger mirror size also means that it has a higher resolution, about 2 to 3 times that of the Hubble Space Telescope, which is also very useful for high redshift astronomy as well. Currently, the observations for its first year of science observations are planned. So these science observations are going to start in June or July of this year and last the entire year, which is called Cycle 1 observing. And I'm just going to talk a little bit about some of these observations and what we expect to get from them. So the first kind of observations I'll talk about are the director's discretionary early release science. There are several different kinds of observing programs or ways that you can get time to observe on Webb. And this is one of the very, very important ones. These observations are going to be taken during the first 5 months of Webb's science operations, and they will be immediately released to the community for analysis. So anybody in the world can access this data and use it in their own research. They don't need to be affiliated with Webb for that. And this is a pretty useful thing because it gets people used to dealing with Webb and also have a better understanding of some of the things that it can do. So the results of the director's discretionary early release science will be used to plan for future observations. In terms of high redshift astronomy, the things that it's going to do is it's going to make some initial catalogs of the highest redshift galaxies ever found. So galaxies at redshifts greater than 9. And also do deep spectroscopic observations of galaxies over redshifts 6 to 9. Apart from that, there are many, many other fantastic observations that will take place with the Webb telescope, which I can briefly go over here. So it will first of all do a census of galaxies during the epoch of reionization and out to redshifts 8 to 10, which we desperately need. It will massively expand on our sample sizes. It's also going to find and characterize galaxies up to redshifts 15, so the highest redshift galaxies that have ever been found, and even possibly beyond that. It could detect higher redshift galaxies, which would be fantastic. It also includes many wide and deep field imaging programs. The wide field imaging programs will do imaging and spectroscopy on millions of galaxies. They'll be used to study unique and rare objects during the epoch of reionization. Used to be to study galaxy evolution and also study the structure of the universe at high redshift. So it's going to be looking for clustering of galaxies at high redshift, which are the precursor to the larger scale structures that we see today in the universe. The very deep imaging and spectroscopy programs it's going to do is of a smaller region of space. So it's like the Hubble legacy field compared to the Hubble ultra deep field in terms of size. And this is going to observe thousands of galaxies at high redshift, including many of those that are just too dim to be found using the wide field imaging. Many of these observations are also going to be centered around existing deep fields like the Goods fields or the Hubble ultra deep fields. So Webb is really going to open up a new window to the universe and observe the dimmest and most high redshift objects that have ever been detected. So I'm very, very excited for this telescope. Webb is not the only thing that's not the only amazing telescope that's coming up. There's also the Nancy Grace Roman Space Telescope. This is a 2.4 meter diameter telescope, which is also an infrared telescope, but it only observes wavelengths from 0.5 to 2 microns. It is currently past its design review. The primary mirror and part of the spacecraft is already complete, and if things keep going the way they are now, it will hopefully launch by about 2027. Now, the Roman Space Telescope is often compared to the Hubble Space Telescope just because the pair of telescopes have primary mirrors that are the same size. But the one of the key differences between Roman and Hubble is that Hubble has a focal ratio of f24, and Roman has a focal ratio of f7.9. So this means that Roman can observe a much, much wider field of view than the Hubble Space Telescope can, but at the exact same resolution as Hubble. So it has a 0.281 square degree field of view using the wide field instrument, which is one of 2 instruments on board, but will produce the exact images with the exact same resolution as the Hubble Space Telescope. For comparison, I have a image here of the Nancy Grace Roman Space Telescope field of view in orange. It's in this kind of smile pattern with gaps between several of the detectors. There's also the Hubble Legacy field in white around here, and the Hubble Ultra Deep field in here. So you can see from this image that Nancy Grace Roman images an incredibly wide area, much, much, much wider than the Hubble Space Telescope. And it's actually projected that Nancy Grace Roman, in its first 5 years in operations, will image 50 times the amount of sky that the Hubble Space Telescope has in its 32 years in operation. This is incredibly significant for many fields in astronomy, even high redshift astronomy, just because if you think about how many galaxies were in the Hubble Ultra Deep fields and Hubble Extreme Deep fields, imagine the Nancy Grace Roman Space Telescope does the exact same thing. It does its own version of a deep field, just like Hubble did. It's going to be able to find orders of magnitude more galaxies than the Hubble Space Telescope ever has been able to. It's actually projected to be able to find billions of galaxies, just not particularly at high redshift, but at all redshifts, it should find billions of galaxies just in its first few years of operations. So this is really going to be a fantastic telescope. There haven't been as many things planned for Nancy Grace Roman as they have been for Webb, just because Webb is further along than Roman. But it is intended to be primarily a survey telescope. So there are 4 surveys currently planned for Roman. There also includes guest observing programs where people can apply to use the Nancy Grace Roman Space Telescope for their own work. And there have been some projections just based off of the current surveys planned and some potential future surveys. So it's projected that it could find up to 10,000 galaxies at redshifts 8 to 9, up to 1,000 galaxies up to redshift 10, and find galaxies up to a redshift of 15. So this thing will be able to massively expand the sample sizes of high redshift galaxies that we currently have and will have with Webb. It will also complement the Webb telescope very well because it can do wide field area surveys, pick out galaxies using photometry, so the direct imaging, and then Webb can follow up on those images to get spectroscopic redshifts, which are more accurate than the photometric redshifts. So Roman and Webb will work incredibly well together. Finally, the last telescope I'll be talking about is the Square Kilometer Array. This is a ground-based radio telescope instead of a space-based infrared telescope. And what this telescope is going to do is it's going to use thousands of radio dishes combined with up to 1 million antennas, which are located in 2 countries, to cover over a square kilometer of collecting area. This makes it the world's largest radio telescope ever. And all those millions of antennas and thousands of radio dishes will work together to form one massive telescope using a technique called very long baseline interferometry. This is the same technique that produced the black hole image from a few years ago, just doing it over a square kilometer instead of a telescope the size of the Earth. So what the SKA is going to be able to do is observe for the very first time neutral hydrogen during the dark ages, cosmic dawn, and the epoch of reionization. It's going to observe the 21 centimeter emission line. The 21 centimeter emission line is emitted by neutral hydrogen. The electron in a neutral hydrogen atom can exist in many states, and there's an incredibly small difference in energy between 2 of those states. So when the electron transitions from one state to the lower energy state, it emits a low energy photon, which has a wavelength of 21 centimeters. It's very common to observe neutral hydrogen using the 21 centimeter line for galaxies at lower redshift, but this has never been done at higher redshift. So the Square Kilometer Array, for the very first time, is going to observe the neutral hydrogen during the epoch of reionization. For the very first time, it'll be able to observe cosmic dawn and also the dark ages. This is the only way, really, to observe gas during the dark ages, because there's no stars during the dark ages. There's nothing really emitting light except for neutral hydrogen. So it's expected to really revolutionize our view of that very, very early universe. It could potentially image galaxies or image structures in the early universe up to a redshift of about 30. So some of the main things that the Square Kilometer Array is planning on doing in some of its first years of operations is to identify structures in the early universe. It can study the history of reionization, so how fast it was. Was it a slow or was it a fast reionization? And it will also observe the first stars, population 3 stars. It will observe the neutral hydrogen that they're forming out of. It will also observe the first galaxies and can even observe the first black holes. And another very interesting thing that the Square Kilometer Array can do is it will also be used to plan for future telescopes just like it. So other radio telescopes that have similar designs to the Square Kilometer Array based on similar ideas could possibly image structures out to redshift of 200, so deeper into the dark ages. So the Square Kilometer Array is going to, I think, be a very, very interesting telescope that will hopefully do many, many amazing things for extragalactic astronomy. All right. Well, that was my presentation on high redshift galaxies. Thank you for listening, and I hope it was interesting.
What a great talk. This has definitely left us all thinking. So wonderful, wonderful talk, Senna. The early universe, the earliest galaxies, and of course, what we might hope to get in the future. I have to thank you especially for the SKA and Australia shout out. So wonderful. I'm already thinking of, what I can use it for, and possibly, gosh, maybe making a guest observer request for the Nancy Grace Roman telescope. So lots and lots of wonderful things. Very exciting times. games. And we do have a few questions coming your way all the way over from YouTube. I'm not sure how many we'll get, but I'm going to pass you over to Emma for some questions. So, Emma, why don't you take it away and ask our speakers some questions now?
So we actually got a couple of questions and a couple of comments for the presenter. But first question coming in from Joshua Parsons. Would you expect in the far future, when star formation starts to die down, that the universe will return to being neutral, since there won't be young hot stars to ionize the mix?
That's a very interesting question. I would go with, I think the answer is going to be no, because part of the reason that that the early universe could things could reionize or recombine in the early universe is just because it was a lot smaller than it is now. The universe was only 380,000 years old at the time. It's 13.8 billion years old now, so it's orders of magnitude difference in age and also difference in size. The universe is expanding at speeds greater than the speed of light right now. So at this point, if we turn off all of the ionizing sources in our universe, the neutral hydrogen and other neutral atoms would not be able to recombine and form because there's really just not enough of it. You might be able to have some of it recombine, but it's not dense enough to really be able to do that on the large scale. So it could happen on maybe some smaller scales that have more densely packed matter. But when you're talking about the larger scale universe, there's too much space in between these ions for them to fully recombine.
Thank you. Second question coming in from Aaron Thompson. Are there any particular features in high redshift galaxies that you would expect or hope for the James Webb to reveal?
Lots of them. I'm particularly interested in extreme emission line galaxies. That's what I've been working on. I'm also interested, or another thing that's very interesting would be finding some more evolved galaxies at high redshift. So like I said, the massive and luminous galaxies at high redshift are rarer than small and dim ones. So it would be really interesting to be able to observe some of these more massive and luminous galaxies. And even something that would be incredibly interesting is a galaxy that's not forming many stars. So if you look at lower redshift, there are some massive elliptical galaxies. And it would be very interesting to see some of these, maybe not massive ellipticals, but galaxies like those that aren't forming stars. And if I'm remembering correctly, there is actually some planned observations for James Webb to try and investigate some of these dead galaxies in the high redshift universe and figure out how those form. So that would be a very interesting thing from Webb.
Cool. Thank you. The next question comes in from Ron McNaughton. Is it possible to estimate the number of galaxies of a given redshift and brightness? It makes sense.
Yeah.
They were closer than the 2.5 million light year distance to the Andromeda Galaxy.
Yeah, so it is possible to estimate the density of galaxies based off of redshift. And one related to some of the things I was talking about, one of the big open questions and one of the things that really want to figure out for high redshift galaxies is investigating the luminosity function. So these luminosity functions, you have luminosity functions for every redshift. And basically what they tell you is how many galaxies there are as a function of their brightness. So the current observations suggest that the very, very dim galaxies in the early universe are going to be very abundant, but very, very luminous galaxies will be much less abundant. But there is a lot of uncertainty in the shape of this. So how abundant are luminous galaxies compared to how abundant are dim galaxies? This is in part because of observations of galaxies like GNZ11. It's not really expected that you would be able to see a galaxy that bright and that big that early on in the universe. So that is one of the main questions that astronomers are trying to figure out and will use Webb to investigate. In terms of the actual number densities, like the actual values compared to the distance between the Milky Way and Andromeda, I don't know an actual number value estimate on that, but it is an open area of research in both the number density of galaxies as a function of luminosity and mass is definitely one of the things that Webb will be investigating.
Very cool. You got a couple of comments as well.
Right?
From Johnny, you got, hi, Sunna from Montreal with cousin Doris and family.
Hi.
Harold Locke would like to say, thank you, very clear explanations. Yassine says, great presentation, really enjoyed it. And Chris Vaughn says, thank you. And that's it from questions and comments.
Thank you.
Well, thank you once again, Sana. We could certainly stay here a while talking about, galaxies and, of course, the James Webb Space Telescope. And as just a little rounding off of this evening, I would just like to point out that our speaker tonight, Sana, with Joshua Parsons, who was in chat earlier, actually did succeed in getting a picture of the James Webb Space Telescope from the 1 meter telescope at the Alan I. Carswell Observatory. So look for that on, I don't know, their website later. So huge congratulations. It is a very exciting time for galaxies, for research in the early universe, and for telescopes all over. So thank you very much, Sana, once again for tonight. And with that, I'm going to go ahead and hand over to our president of the Toronto Centre RASC, Tom Luton, to finish off the evening. So take it away, Tom.
Thank you very much, Elena, and thank you very much to our speaker. That was a wonderful talk. So, good evening, everybody, and here are these evening's announcements. So, as Elena said beforehand, we have two types of meetings here online on YouTube. We just had one of our speaker nights, and then coming up in a couple of weeks, we're going to be having our recreational astronomy night. So, for those of you who watching us live, please use the YouTube chat, say hello, enter some questions for presenters like others have done for yourself. If you're a new member, please introduce yourself. And if you're coming from far, far away, please let us know where you're from. So our next recreational astronomy night, like I said, is in a couple of weeks. Andy Beaton will be discussing the sky this month. Michael Cook will be talking about relocating and expanding Newcastle Observatory. And Krishna Videla will be discussing Astronomy Logbook, a 21st Century Stargazer's Pocketbook. Online here at YouTube, please contact Paul Markov if you've got something that you'd like to present. Our next speaker's night is 2 weeks after that, on February the 16th, 7:30 p.m. Vivian Yunyan Tan of York University will be giving the talk. We don't have a finalized topic or presentation title yet, so we'll let you know as soon as we get that. Coming up at the DDO in the next few weeks, on the 23rd of January, 12:30 p.m. is Sunday Stargazing. Registration links can be found at rascto.ca, $6.78 registration fee. On Saturday, February the 11th at 7:30 p.m. is Astronomy Speakers Night. Again, to be announced. $12.50 registration fee. Links at rascto.ca. DDO Up in the Sky is on Saturday, February the 19th, 7:30 p.m. $12.50 registration fee. Again, links on our website. This is where I get to plug our Observing Certificates program. So, if you've had an opportunity to do a little observing in and amongst the occasional blizzard, and you've made some progress for your certificates, please let us know so that we can, if you've completed it, please let us know so we can get your paperwork dealt with and send you one of our lovely pins that we've got here on the side of the slide. And if you haven't this is something you want to think about. It's a wonderful way to learn the night sky. We've got a whole bunch of different programs: Explore the Universe, Explore the Moon through binoculars or telescopes, Messier Catalog, the finest new general catalog objects, Double Stars, the Isabel Williamson Lunar Certificate, Deep Sky Gems, and Deep Sky Challenge. Full details at www.rasc.ca/certificate-programs. Now, as a broken record, once again, our observing sessions are still suspended until further notice. So all the ones at Bayview Village Park, the Long Sault Conservation Area, and at the Ontario Science Centre. The Carr Astronomical Observatory, total site occupancy is currently limited to 10 bookings and up to 25 individuals, with one member or family upstairs in the house and the rest as members. Excuse me. The rest members and families bookings for day use or independent campers or using an RV or tents. Full details are on the website. Please read everything before you make a booking. This is where I get to plug Rask membership. Renewal can be done online or sign up for the first time at secure.rask.ca. If COVID has thrown you for a loop, we do have an emergency fund. It's confidential at members or at mempub at rask.ca, and as well, gift memberships are available. And with that, I'd like to wish you all a very good evening and a good night. Thank you very much for joining us. You can follow us on all the forms of social media we've got listed here. If you like what you saw here on YouTube, please like and subscribe. Click the notification bell for future updates. Be safe and keep looking up. Good night.